Alright, now we're in limit. This, you can expect to see problems like this on the no calculator section. Some of them may be on the calculator section as well. So here we need the limit as h approaches 0, which makes this h in the denominator a problem. That should be kind of a red flag for you. If you have an h in the denominator, you can't just plug in there. So we've got some work to do, some algebra work. I'm just going to do all this stuff as scrap work. And when I'm ready to evaluate the limit, I'm going to come back here. So 3x plus h squared, I'm going to rewrite like this so I don't make any mistakes there. Minus 3x squared all over h. So I have my 3 on the outside, and I need to expand this binomial. So that's x squared, xh, another xh, so it's 2xh, h squared. Everything's positive. Those parentheses are important because it's 3 times that whole thing. So the next thing we'll do is distribute that 3 in. Again, I'm not evaluating the limit. I'm not carrying the limit notation because I'm just kind of doing this as scrap work. Just simplifying it. So that's 3x squared plus 6xh plus 3h squared minus 3x squared. And my x squareds cancel. My 3x squareds, I have one positive and one negative. And I have h's on top and an h in the denominator that I can cancel. I'm going to factor before I do that. Just to make sure I take it by both places. So algebra with limits is dangerous not because the algebra is that challenging. It's because there are a lot of places where you can make mistakes. And knowing to multiply out there instead of just squaring your x and squaring your h, just precision is a thing. It's an important thing. So this whole mess reduces down to 6x plus 3h all over 1. We got rid of that denominator. And now we can put our 0 in for h to evaluate the limit. 6x plus 3 times 0, which makes this whole thing 6x. And the answer is D. Alright, if that was too fast, of course, rewind, pause as you need to, and pick up the steps that you were missing. Alright, another limit and some algebra. So we can't plug in the 3 in this complex fraction. We need to deal with our complex fraction first. I'm going to go ahead and just copy that down here. And I'm not going to write the limit notation. I'm going to leave that for up here. That's not something you have to be worried about on a multiple choice test, but it is something that you're going to want to worry about in calculus or even next year. Just showing your steps in a nice way. So in my numerator of this complex fraction, I need a common denominator. So I'm going to multiply each fraction by the other denominator. So my first fraction here, 1 over x, I'm going to multiply by 3 over 3. My second fraction, I'm going to multiply by x over x. My denominator is not going to change. My numerator is, I have 3 minus x over 3x. Lovely. And I'm going to keep going here. So I have, now you can group or you can flip the second and multiply. I like to group. If you don't like this, pause and flip the second and multiply, but leave everything in factor form. Don't actually distribute. So the top of your fraction is 1 times 3 minus x, so just 3 minus x. The bottom of your fraction is 3x times x minus 3. And this x minus 3 was the whole problem. That's the whole reason we couldn't just plug in 3 and go on with life evaluating this limit. But if you look at the top here, it's very similar. Like so similar that if we pulled out a -1 and flipped those signs, we would have -1 times x minus 3 over 3x times x minus 3. And we would be able to cancel those x minus 3. That's the algebra that we need to be able to do in order to evaluate this limit. Now this limit is definitely able to be evaluated. We can plug in 3 and not get a 0 in our denominator. So I have -1 over 3x is what I'm actually going to evaluate here. I can drop the limit notation when I plug in. And 3 times 3 is 9, so I get -1. B. You have to be very precise when you're working through the algebra that goes with these limits. Double check as you go. 38, you just have to know that you can plug in a 0 here. We can plug in a 0 as an exponent. And actually, 0 is arguably the nicest exponent because anything to the 0 power is 1. So that whole fraction becomes 1. So the limit as x approaches 0 of 3 times 4/7 to the x is just 3. All right, let's get one more problem on this video. Oh, and this one has lots of nice factoring. This one I'm going to go ahead and carry this limit notation through to show you how it would look if you really were going to do this in a very linear fashion. We have to use the limit notation if we're not kind of taking our problem and doing the scrap work off to the side. We have to use our limit notation all throughout. So x to the 4th minus 1 is a difference of squares. And we've gotten pretty good at those. The thing is, though, so is x squared minus 1. X squared minus 1 is x plus 1, x minus 1. And I'm not going to break down x squared plus 1 anymore. It is prime. So there's my numerator, fully factored. My denominator is the difference of cubes. So cube root of x cubed is x, cube root of 1, a squared, ab, b squared, and then the part you guys like, same sign, opposite sign, always positive. So that pattern, a, b, a squared, a, b squared, same, opposite, always positive. Just write that out for you. And that a and b come from the cubed root of that term. B is the cube root of the second. Alright, let me make that pretty now. So x minus 1, x squared plus x plus 1. Again, we can't plug in 1 right now because of that x minus 1 in the denominator, but we can cancel it since we've done all of this lovely factoring work. And once we cancel, we can plug in the 1 and we won't get that 0 in our denominator anymore. You can drop the limit notation when you're ready to evaluate. And by evaluate, I mean plug in that 1. It's one of those problems with a billion of the same number. So I have 2 plus 2, or 2 times 2 in the numerator. There's 3 in the denominator. The limit of that rational function is 4/3.